as the higher up you go, the more cosmic rays there are since there is less atmosphere. And if you notice these circles and the triangles, those are actual experimentally observed errors in cache and main memory. If you notice, they align exactly with the prediction for the cosmic ray flux. Now, this IBM study ran from 1978 to 1994, so it's entirely possible newer generations of RAM are differently affected, but cosmic rays is definitely something you want to consider. So, what's the distribution of various causes of bit errors that I see in the wild? Honestly, I don't really know. I can't go halfway around the world and see what was wrong with somebody's iPhone, and it's entirely possible it's a cause I didn't consider. What is interesting to know is that these bit errors do happen, and they're real. We've mentioned DRAM for a bit, and I'm going to go into a little more in-depth discussion about DRAM. DRAM is the source of really great information density for bit errors to happen. It's hard to cool, the components are always cheap, and it happens to be where the previous majority of bit error studies have focused. So, I'll start off with some really good news. And the good news is that all errors in DRAM can be fixed by use of what is called ECC, or error correcting codes. And ECC can detect and fix all single-bit errors. There's actually forms of ECC that will detect all 1, 2, 3, and 4-bit errors. But ECC only works if you actually use it. A lot of you in the audience probably manage extensive server farms, and those typically have ECC memory, since hardware manufacturers know that bit errors do happen, and especially high-end ones. But have you thought about all the RAM in your server? I'm going to go with no. This is a hard drive pulled from one of these enterprise class servers with ECC memory. That chip there highlighted in yellow is 128 megabit DRAM. It does not have ECC. And this drive is actually a few years old. It only has 16 megabytes of cache. Newer drives have 32 or even 64 megabytes of cache. And enterprise servers typically have 5 to 8 of these drives. So the data in your enterprise class server may be going through a lot of non-ECC memory. Let's look at some DRAM failure rates. Now that we've established there's probably a little bit of it in your server somewhere. This slide summarizes 2 different studies, one from Terrazon Semiconductor and one from Schroeder at the University of Toronto in association with some engineers from Google. And the first thing you notice is that the scale varies very widely. This is also a logarithmic scale. The lowest error rate is about 50, and the highest error rate is about 100,000 failures in test. And a failure in test is about 1 error in 1 billion operating hours. Another interesting thing of note here is if you see the manufacturer 1 to manufacturer 6 columns, those are from the Schroeder study, and those were bit error rates measured in actual servers in Google data centers. One of their conclusions was also that the vast majority of bit errors could be attributed to specific DIMMs, counteracting the IBM study and in fact suggesting that maybe manufacturing defects are in fact the #1 cause of DRAM failures. But we don't typically think in terms of 1 failure in 1 billion operating hours, so let's put this in a more usable perspective. If you go to Dell.com, the cheapest PC you can buy will have 4 gigabytes of RAM. Assuming the worst case scenario from the previous slide, that PC will encounter approximately 3-bit errors per hour. Assuming the best case scenario, it'll encounter approximately 3-bit errors per month. But also, it's not right to think of just a single PC. What we want to see is the emergent effect of all the DRAM on the internet. And there are several studies that say that there are approximately 5 billion devices that are connected to the internet in 2010. Assuming each of these devices has 128 megabytes of RAM, and now this assumption isn't really based on scientific fact. I felt it was a very fair compromise between the servers that have multiple gigabytes and your phone, which may have 6 to 20. You will get approximately 600 petabytes of DRAM that is connected to the internet. And using the lower end error estimates from the previous slide, That's approximately 600,000 bit errors that occur daily in all the world's internet-connected DRAM. Now, how many of those errors actually happen somewhere that is interesting? Well, I set up an experiment to find out. And this experiment is in 3 parts. Part 1, register domain names. This list includes actual domain names that I registered. They are 1 bit away from certain very popular domain names. By 1 bit away, I mean is you take the domain name, then you put it in its ASCII representation, you expand it out as a binary string, change 1s to 0s and 0s to 1s. If it's still a valid domain name when you put it back to ASCII, you register it. And the domain names I picked tended to be those of popular websites and, more crucially, advertising and content delivery networks. And the reason they picked those is because nobody ever types those addresses in, but you certainly look them up an extremely large amount of time. Experiment step 2 is you have to properly answer DNS. And this is actually very important, and I'm going to go through this via an example. So let's say somebody out there is trying to resolve a domain name you registered. Let's say it's mic20soft.com, 1 bit away from Microsoft. So you're going to get an A record request, and of course you'll answer it. But the trick here is that we think that a bit error happened somewhere on that server that asked you for the domain name. Therefore, we will also send it back a second reply for the original domain we expected it to be. And the reason we do this is because if it's expecting a reply for Microsoft.com, it will discard the reply for mic20soft.com, but silently accept the Microsoft one. If it did indeed query mic20soft.com, it'll accept that reply, but discard the Microsoft reply. In an overview, for every DNS request you receive, you have to send back 2 responses. And this isn't just A records. This is also other types of records, such as NS requests. Assuming your bit squatting was successful, next thing that's going to happen is you will get an HTTP request. So you set up an HTTP listener, and you log the connection. And in this case, I chose to return HTTP 404 not found for every single request I received, since I wanted to avoid causing any damage to any of the requesting computers. Once again, you get a request, you log the request, you send it back a 404, and you close the connection. Then this is how I set up my experiment. And the first thing that's really surprised me is that people actually show up. This is the traffic volume of raw HTTP requests for a 6-month period from the end of September to the beginning of May. As you can see, there is a steady background stream of requests punctuated by several extreme spikes, the biggest which was approximately 3,500 HTTP requests per day. But raw requests isn't necessarily a fair comparison, since maybe some machines out there get in a loop and you have one guy requesting the same resource over and over again. So here instead is the traffic volume by unique IP address per day. Some of the peaks disappear, but others still remain. Aside from the steady stream of background noise, there's 3 major events labeled here as A, B, and C. Each of these caused by bit squatting, and I will get into detail of these in the next few slides. So, what caused event A that affected more than 1,600 unique IPs on the internet? And that critical application happens to be Farmville. Yes, I'm serious. The reason this says 1,300 IPs is because I could only attribute 1,300 of those directly to Farmville, but the other 300 are also of similar causes. So, how exactly does this happen? Well, let's diagram this out. Let's pretend you're a user somewhere and you want to go play some Farmville. Then you request some stuff from Facebook, and a bit error happens in either the Facebook or the Farmville servers, and profile.ak.fbcdn.net changes to pbofile.ak.fbbdn.net. I happen to own fbbdn.net, and this bit error happens to happen in the URL of an ad server. And this URL gets cached and then served up to the 1,300 people who keep requesting that resource. Instead of requesting ads from Farmville, they're requesting ads from me. I could have sent them anything I wanted, but I chose the 404. Once again, an overview. You're doing nothing wrong, going to play some Farmville. A bit error happens somewhere outside of your control in either Facebook or the Farmville servers. This bit error gets cached, served up to 1,300 people, and those 1,300 people request ads from me instead of from Farmville. And that's event A. And event B was 456 unique IPs. And the cause of that was also Farmville. The reasoning behind it was actually also pretty much the same, except the bit error here was different. You would play Farmville, bit error changes fbcdn.net to fbgdn.net. Once again, this bit error gets cached somewhere in the Farmville cache, gets served up to 130 different people who request ads from me. And of course, you don't have to send them ads. I chose to send 404s, but there's no reason somebody malicious couldn't send them some choice JavaScript. And that's it for event B. And event C is actually the most interesting one of all. And I promise it's actually not Farmville. And it affected 246 unique IPs. What's interesting about event C is that it's an actual case of DNS poisoning caused by random bit errors. And I haven't, after looking through the logs for the days of event C, I noticed that all of the requests for those few days were, 1, from the same /24, and 2, they were all for the same server. And here is approximately what happened. So, you're someone in that /24. You request your ISP to resolve s0.2mdn.net. A bit error occurs somewhere in your ISP's recursive domain server. Instead of requesting s0.2mdn.net, you request to resolve s0.2-dn.net, which I happen to own. If you recall from before, we always send 2 DNS replies. One of the replies we're going to send back is for s0.2mdn.net. This reply is going to, 1, get cached in the DNS server, and 2, get propagated to the original requestor, who will then request an ad from me instead of from 2mdn, and I will send him a 404, but of course you can be more creative. As a full overview of the entire process, you're browsing some website, you request an ad. Your local ISP's DNS server cache happens to be empty. It queries instead s0.2-dn.net. I own that. I answer DNS authoritatively for it, and I say, hey, here's the IP address for s0.2mdn.net. That gets propagated, that gets cached, propagated to the original requester, and now everybody in that /24, when they're requesting s0.2mdn.net, will instead get my IP instead of the original one until the DNS cache expires. So that concludes the 3 outlier events. And if you look at the traffic without outliers, you see that it's generally just a random trickle of requests. But even this, you can see by the blue line that there's an average of 59 requests. This is 59 requests with only 32 domains. This can easily be linearly scaled up by any sort of organized person. Next thing I wanted to do after measuring the traffic volume was to see the volume per hour. My intuition here was that there would be more bit errors when it's hotter outside during the day. Unfortunately, it also turns out that most people use their computers during the day, so it's impossible for me to separate the causes due to heat from simply more traffic use.